SwayamPrabha. Digital India. Educated India.
Hello, we are continuing to discuss about the linear viscoelastic models. We are only focusing on linear because this being an introductory course where the aim is to give you a flavor of how the viscoelastic analysis is done. But now the pertinent question to ask is, how do we define a particular polymer is linear or non-linear? So, or what are the conditions under which we can say so and so particular polymer is behaving as a linear viscoelastic material? This linear viscoelasticity we can define if it meets two conditions. One is the superposition and the second is the proportionality. So, in this video we will go into details and see or try to understand when a particular polymer meets this superposition and proportionality. So, let us start with superposition. So, even when we discussed about linear elastic materials, we discussed about superposition. So, if you remember, let us say deflection of beams, let us say we had a cantilever beam which had two loads, one at the free end, let us say P1 and one somewhere in between P2. And let us say we are interested to know what is the deflection happening at the free end. So, at this length, let us say this is the length L. So, we are interested to know what is the deflection happening at length L or at this point. Since we were discussing about linear elastic materials, we said this can be solved if you know how to solve a deflection of a beam with one single load. So, the way we said is it will be simply superposition of two problems, first with a single load at the free end which is P1 plus the same problem solved with the intermediate load P2. So, from both these problems we find what is the deflection of at point L because of the load P1 and deflection at lower point L because of the load P2, and the total deflection is we can simply superpose and get these as the sum of both because of load P1 plus deflection because of load P2. The same concepts we can also apply to viscoelastic materials, and the reason why this superposition is very powerful is because now it helps you to analyze arbitrary loads or nonlinear loads. So, let us start by looking at a particular load. Let us say with time we have a loading in the rate of in the case of stress varying sigma t. So, let us say it starts with a non-zero value and it is increasing. Let us say the starting value is sigma naught. So, we can represent this nonlinear load input as a series of step functions. So, in this case, since the load is the stress, this step function will consider it as creep loads because in creep the input is constant stress. So, let us try to write this stress input sigma of t. Since we said we will now attempt to write it in terms of step functions, we will start with having a step function at time t equal to 0 with an amplitude of sigma naught, right. So, it can be written as sigma naught times h of t. Then let us say at a time t equal to t1 we will consider a step. And then another step function. So, which means what is the amplitude of this step? we have already considered sigma naught. So, from sigma naught it is going to the stress level sigma 1. So, which is sigma 1 minus sigma naught, which is the step sigma 1 minus sigma, and then the Heaviside function now applied at time t1, t minus t1. And now I can take another step. Let us say the corresponding stress is sigma 2 at time t2. So, of course, one can now write it as sigma 2 minus sigma 1 times Heaviside function applied at time t2. Now, I can have as many steps as possible, like this can continue. What we are trying to do is, with these steps we are trying to capture the input curve, and looking at this the nature of this expression, we can write it in a more general form as sigma n minus sigma n minus 1 times h of t minus Tn. Okay. So, one might say, okay, though we are using these steps, it is not actually touching the curve. The way to address that is, now we say these time steps, what we are talking about t minus t1 minus t, or this t2 minus t1, let us say this is some epsilon value, which means it is very small, and what happens if it tends to 0? When it tends to 0, these steps will approach the function what we have applied. Okay. So, what we are trying to show here is, if we have an arbitrary load, that can be represented using these step functions, and here we took help of these Heaviside functions. But now that we say that the superposition is applied, because now we are talking about linear viscoelastic materials, how can we write the response? So, the response is, we need to know what is the strain response because of the stress load. So, to help us write this, let us recall how we looked at the response for a creep load. So, a bit of recap, we are saying that for creep load, the input is sigma of t is sigma naught times the Heaviside function. And what did we say the output? The output we have written in terms of the creep compliance. So, strain is sigma naught times the creep compliance represented using d of t, right. And similarly, if we say that the input is not exactly at time t equal to 0, but at an arbitrary time t1, that can be written as a Heaviside function of t minus t1 multiplied with this load sigma naught. For this, what is the output for a creep load? We said the strain can be written as sigma naught times the compliance function evaluated at t minus t1. So, with this information about the creep response, now let us get back and see what is the response to this arbitrary load. So, we will go one step at a time. The first step is this sigma naught times h of t. So, from this formula here, we can write that the response is sigma naught times d of t, the creep compliance for step load at time t equal to 0, plus sigma 1 minus sigma naught times again the creep compliance at time t minus t1. So, similarly, sigma 2 minus sigma 1 times d of t minus t2, so on and so forth, and to write this general term, we write it as sigma n minus sigma n minus 1 times the creep compliance at Tn. Yeah, bear in mind that each of these terms in the response is again there is a step response in this. What I mean is these responses start, for example, for the first time they start at time t equal to 0, second term the response starts at time t1, t2 and so on and so forth. So, here what we are seeing is how can so first of all saying that the linear viscoelasticity means it should follow this superposition, and once we know that the superposition is valid, we can be able to write any arbitrary input in terms of these step functions, and then we can invoke these creep compliance to write what is the strain response. But bear in mind I have shown this example assuming that the loading is stress. What happens when the loading is strain? So, what I mean is, let us say we are looking at an input where with time strain changes, and we are saying that this is the input. So, how do we find the output here? We identify this problem as, again we will use this superposition and we will invoke writing this input as a series of step functions, but now we will identify that we will be using the relaxation modulus or the relaxation loads. So, meaning that this epsilon of t, which is the input, is written in terms of epsilon naught times h of t, which is a relaxation load, plus the other terms. And again when we write about the response, the output, and this is the input is the strain and the output is the stress. When we write this, we can now write it in terms of relaxation modulus, E of t plus the next step will be epsilon 1 minus epsilon naught times E of t minus t1 and so forth. Okay. So, we have now seen the first condition of linearity, but now let us also look at what is the second condition of linearity. We now talk about proportionality. Proportionality for a linear elastic material means your modulus is written simply as E, which means it is not either a function of neither time nor stress nor strain. So, this is the thing with linear elastic. For linear elastic, it is neither a function of time, stress or strain. What do I mean by stress or strain? When we look at the stress strain plot and we said this is the response of the linear elastic material, we are only talking about the slope of this curve when we discuss about modulus E. That slope does not depend on what value of stress we are discussing. So, it could be sigma 1, it could be sigma 2. No matter what sigma or the stress value you are taking, sigma 1 or sigma 2, the slope remains constant, which means your modulus is independent of the stress applied. Same thing with the strain. So, it does not depend on whether these points are epsilon 1 or epsilon 2 or the strain 1 and strain 2. This is what we meant by linear elastic. But now when we talk about the viscoelastic materials, we need to be a little careful in defining this. When we talk about the creep compliance, we say that it is independent of applied load. What is the applied load in creep? It is stress. And similarly, if we are talking about relaxation modulus, we say it is independent of strain. Strain is the input. But these are the definitions of proportionality, but let us say we have a material at hand and we need to understand whether it is behaving like a linear viscoelastic material or not. For this one need to do a series of tests or a more rigorous amount of testing to first comment on whether it is linear viscoelastic or non-linear viscoelastic. Now let us carefully look at the one kind of experiments one can do to determine whether it is linear or non-linear. So for this we will do one can do either creep load or a relaxation load, but let me start with creep loads. So we need 3 tests. So let me take 3 inputs. So since it is creep, the load is stress varying with time. Since I said there is 3 tests, let me also. So the difference we do in these 3 tests is we will change the amplitude of the stress which is applied. So initially we will start with sigma naught. Let us call this as sigma naught A to distinguish it from the other 2 tests, because the other 2 tests we are saying will be at a different stress level, like we will call it as sigma naught B, and then another stress level slightly higher, sigma naught C. So that is the difference in the load input for these 3 tests. Now let us look at the experimental responses we are expected to see. So what is the response? Our response what we are looking at is strain now. Okay. So how do we expect this response to be? So there will be some instantaneous strain because there is a non-zero stress applied at time t equal to 0, and then the strain keeps increasing. So let us say it is somehow like this. Okay. Now what we will do is we will note the strain values at 3 different times. Let us say we are looking at time t equals t1, time t equals t2 and time t equals t3. So essentially we are looking at these points. Let me use different symbols at different times. So this is a star, maybe a circle here and a triangle here. Okay. So and then the corresponding times, let us also look what is the strains. So this will be at time t1 and this will be at time t2 and time t3. So again the same notation. Okay. So this is the response we observed from the first experiment where the loading is relatively low. Now let us look at second experiment and see what is the response. So again here too you will have an instantaneous response, but this value, the strain at the initial strain will be slightly higher. So let us say it starts from here and then again it shows this kind of response. So we are again looking at times t1, t2, t3, the same times. At time t1 we use a asterisk, circle, triangle, and the correspondings in the strain response at time t1, t2, t3. Okay. Now coming to the last test. Now that we have increased the load value, even the response will be higher. Now looking at these 3 different times, T1, T2, T3. The corresponding strains are shown here. Okay. Now we have seen these 3 experiments. Let us say these are experiment A, experiment B, experiment C. The only difference is the amount of stress we have applied in A is the least and C is the highest and B is in between. And for this we have looked at the what is the response at each of these loads. Now what we will do is we will try to plot it in a single graph. And how do we plot it? So we want to plot the stress strain response. So let me take a different color now. So let us say we are looking at the stress and strain. So let us plot these. Let us start with the first experiment. The first experiment we said these are the stress is remaining constant. So at this stress of sigma naught A, there will be 3 different strains. We have looked at 3 different times. So let me show them as for time t1 is the star, circle and the triangle. So now let us see the results for the second test. So now the loading is at sigma naught B and let us say the responses are somewhere here. Okay. Now moving on to the last test. The load value is sigma naught C and the corresponding strains are somewhere here. Okay. So basically what we have done is we have done 3 tests. So there is an input stress and there is an output strain and we have plotted those 9 points. For each test we had 3 different times. So these are the 9 points. Now let us try to comment on whether this material is linear or not. We say that this material behaves linear when for a single particular time. So when we fix the time we call this as isochronous. We have already looked at in few videos earlier. So we are now looking at isochronous behavior, which means let us focus on time t1. So we have these 3 plots and if we connect them they more or less fall into a straight line. If they fall into a straight line then we can conclude that at time t1 the response is linear. Similarly at time we are talking about time t1, so let me write it here. Similarly for time t2 we again see that there is linearity between the responses at the 3 different loads. This is at time t2. Same thing with time t3. So if these responses are no matter what we are looking at 3 different loads, they all fall on a same line when we are looking at constant times or we are looking at isochronous behavior, then we can conclude that the material we are looking at is linear viscoelastic. So, let me elaborate a little. So, now let us see what happens to the creep compliance. So, let us say we are writing creep compliance of d of t. Let us focus on the first experiment, and for the moment let us say we are looking at time t equal to t1. Okay. So, how can we write the compliance from the first experiment? First experiment we are focusing on this point. So, it will be simply strain at time t equals to t1 divided by the load sigma naught A. Okay. And from the second time, now for the second test, how can we write it? So, it is at time again t equals t1, but the load is sigma naught B. And finally, for the last test, strain at t1 by sigma naught C. So, essentially what we are saying is this slope, the slope of this curve, which is represented as d of t1, will be the same for the test 1, test 2 and test 3, where we are changing the stress levels. So, which means we are coming back to the definition of proportionality and saying creep compliance is independent of what is the load? The load is stress here. Okay. Same thing we could have shown for different times T2 and T3. So, again as the case with superposition, in this proportionality we have taken an example of creep load, but as well one could repeat this test with instead of creep the relaxation test, and then they need to check whether the creep the relaxation modulus is independent of strain, again using similar analysis. So, usually what happens is it all depends on the kind of strains we are looking at. If we are limiting our strains to let us say within 3% or 5%, most polymers exhibit this linear viscoelastic behavior. But if you are looking at strains beyond that, that is when the nonlinearity kicks in, and then the if we are plotting these isochronous plots, we will see a curve and we do not see a straight line. So, this should explain us the two essential conditions one needs to check whether before one can apply this viscoelastic analysis or the linear viscoelastic analysis. First is the superposition and then is the proportionality. But when these both are met, we will show in the coming videos how one can take advantage of the solving of the equations become easy. We will look at in the next slide. Till then, bye.